So howdy everybody. I'm going to talk about something that people have not, have not actually talked about a lot in Kubernetes world until very recently, which is performance. And I mean, a lot of it just has to do with we've been spending a lot of time building up functionality, and performance is irrelevant if you can't do the things you wanted to do in the first place. And so now we're getting to the point of being able to do all the things. We're looking at other areas. But first I want to actually make a little disclaimer, just to make sure that nobody's going to be disappointed and nobody's in the wrong talk. The description of this talk said I would be talking about both own hardware and cloud performance. This talk was slotted in as a last-minute replacement for a cancellation, and I did not have time to integrate my latest cloud performance information into it. So during this talk, all I will have in my slides is own hardware performance. I can take questions about cloud performance, though. So, that out of the way, let's talk about a few things. So, first thing people say is, hey, why are you even talking about this? Isn't Kubernetes just for stateless applications? And there are some people who firmly believe that Kubernetes is just for stateless applications. As a matter of fact, historically, Kubernetes was just for stateless applications. If you started with Kubernetes 1.0 or earlier, as I did, there was no way to get it to work for anything that needed storage without really hacking Kubernetes itself. That's changed a lot. We've added a whole bunch of different things to Kubernetes, both core features like stateful sets and volume snapshots and local volumes, and a whole bunch of plugins and other Kubernetes ecosystem things in order to make Kubernetes an effective orchestrator for applications that need state and storage. And this has resulted in a lot of people moving their stateful applications to Kubernetes. In dev, in testing, and in production. But there's still a few roadblocks. Still a few things that don't work great out of the box, that people run into out of the box as problems. Now, these roadblocks generally fall into three different areas. One is management. That is, how do you manage your storage and your other repositories of state across the cluster, particularly in the event of failover or redeployment or a whole bunch of other things. Second is storage setup complexity. That is, I would say it's not significantly harder to set up your storage in Kubernetes, but for a lot of kinds of storage, it's not any easier either. And it wasn't exactly easy in the first place. And the third is performance, which is what we're going to be talking about today. Now, for storage setup complexity, we've made a lot of progress by extending Kubernetes itself through things like the Rook operator, which does actually greatly simplify setting up certain kinds of storage. For management, UI, UX, that sort of thing, haven't made a lot of progress, sorry. Like I said, all I can say is it's not like setting up storage was easy. It's not like running storage, like running stateful applications, required zero expertise before. But then we come to this last one, performance, which is what the rest of this talk is about. Now, people say, why does performance really matter in this context, right? Just add more servers, whatever. Well, I mean, I will tell you, system administrators, ops staff, DBAs, that sort of thing, they do care about performance because extra machines or extra cloud instances are expensive. And if you need more of them, then it's a problem. There are a whole variety of options, which I will be exploring in this talk, that allow you to trade out various gradations of ease of use for raw speed, which is a trade-off that is familiar to people who work in the ops sphere. How many people here, by the way, are a system administrator or database administrator or ops? Yeah, okay, yeah. So you understand, right? You're always making trade-offs on, hey, this platform is really simple and it's point and click, but it's dog slow. That's the trade-off you always make, and you can make those same kind of trade-offs inside Kubernetes, but you need to know what the trade-offs are, not just qualitatively, but numerically. And then the other thing is, performance can be a migration roadblock, right? Because you have an SLA that you need to meet, and no matter what other advantages that Kubernetes brings to the table, if your database can no longer meet its SLA once it's running on Kubernetes, you can't migrate. So it's an important thing to answer. And so I and a bunch of other people were working on answering. We're forming a sub-project of SIG scalability in Kubernetes to actually address application performance, because we care about this. Other reason I care about it, of course, is that I worked on PostgreSQL for 18 years. I've worked on database benchmarking and stuff. Spent about 10 years in TPC, et cetera. So I'm familiar enough with benchmarking that I actually find it fun. So, oh, by the way, there's that word benchmarking. Let's talk a little bit about that. Has anybody here actually done any benchmarking? A few people. Okay. So for the people who haven't, one of the things I want to say is important about benchmarking and something that people get wrong is they think of benchmarking in terms of, hey, I'm trying to achieve a number, which is actually wrong. Because what you're doing when you're benchmarking is you are trying to compare things. You are trying to say, hey, if I have this on direct attached storage, how does it compare to having it on distributed storage? If I have this running on Kubernetes 1.16, how does it compare with Kubernetes 1.18? If I set this up with 3 copies of each shard on my Ceph storage, how does it compare if I have 4 copies of each shard? And most importantly, how does all of this compare against the SLAs or SLOs I am already required to meet? So what you're really looking for is to take 2 or more things, or a lot more things, and compare them using the benchmark as a tool. Now, I also want to talk a little bit about the types of storage that are available to us in our sort of cloud native environment, right? You have your straight up, I'm just going to use the machine storage. We have some more Kubernetes advanced usage of node local storage, which I'll explain a little bit more about. You have network storage, and again, this is going to be like various things. It can be within a local environment. It can be iSCSI. It can be NFS. It can be something like that else. Within a cloud environment, you're going to always be using network storage. Pretty much all storage in public cloud is network storage. And then we have what we call cloud native distributed storage. The paramount example of which being the Rook-Ceph combo. But this means that your cloud both hosts the storage and provides it. And it has some advantages. And again, talk a little bit more about that later. But these are sort of types of storage. Now, because today's talk is going to be about my own hardware, my hardware setup, I am skipping the network storage part of the comparison. As opposed to on public cloud, where it is all comparison against network storage versus ephemeral storage versus other things. So instead, we're going to compare local storage running off of Kubernetes, on Kubernetes, and then cloud-native distributed storage. Now, I also, because most people haven't done benchmarking of storage and other things before, I also want to explain a little bit about what we're looking at when we look at storage performance. So we have 4 different activities that we can do in terms of the computer system interacting with storage, right? You have random reads, which is get me this 1 block from disk, and random writes, which is write this 1 block to disk. You have sequential reads, which is, hey, I want to read this gigabyte all at once, and sequential writes, which is, hey, I'm going to write out 12 gigabytes of data to consecutive sectors if you're on spinning disks, or who knows where if you're on SSD. And these have notably different behaviors to the point where systems can be faster at one and slower at the other. And depending on what you need out of your application, it's important that you optimize for the kind of storage activity you're going to need. Like, for example, if you're running a small database, you're going to do lots of random reads and random writes, and therefore you want a system that performs well for that. Whereas if you're running, say, video streaming, you're going to do a lot of sequential reads and writes, and it's more important to optimize for that. And some storage systems really do trade that off. So now, because random reads and random writes are so often a combination, you know, write 4K, read 4K, generally in benchmarks these are tested together. And so you'll see when I give you the figures, it's a figure together, whereas sequential reads and sequential writes tend to be different activities and separate processes. Now the other thing that I'm going to talk about is there's two different ways that we measure storage and memory performance, right? One is latency, which is how long does it take to start getting results after I make a request. And the other is throughput, which is how many requests or how much bulk data can I move per second, per minute, per whatever. And again, these two things not necessarily vary together. You can actually have systems that have high latency but great throughput, or vice versa. So, 18 different combinations here. We kind of want to test all of this information. Fortunately, there is a large body of tools and information to do this in the form of database benchmarks. Because database geeks care about performance deeply, because they are constantly under pressure from the businesses that they work for to make the database faster. And so they care about performance. And one of the nice things about the database is it tends to actually hit all of the systems. It tends to use CPU and memory and storage all at the same time. Plus, we have all of these different tests that we can use that already give us a very rich set of information about how our system is performing and what kind of actual latency and throughput we're experiencing in different combinations of actions. I'm going to introduce you to a few tools here. There are actually a lot more out there. It's lovely. A lot of them are open source. A lot of them are easy to use. Again, because I didn't have a chance to update these slides for the slot, one of the ones I don't have in here is for a Kubernetes only experience, the Kubernetes benchmarking operator, Ripsaw. Which, if you're only going to check within Kubernetes and not outside Kubernetes, inside Kubernetes, can be a really easy way to do benchmarking of your cluster. But sysbench is an old tool. Oh, by the way, they're right. Sysbench is an old tool created by the MySQL folks. It does a variety of different I/O tests plus database performance tests. I'm going to show just the I/O tests here because I'm going to show database performance with PostgreSQL's pgbench, which ships with Postgres, which is a transactional database test. And then CockroachDB, when they launched, they released a bunch of these useful workloads based on industry benchmarks. Unfortunately, like other portions of CockroachDB, these are now under a non-open source license. Just if you're using them, you need to look at the license that you're using. We're going to do some checking of direct file I/O with sysbench. Now, sysbench does have database tests. It has some other tests built into it. You can see, look at the sysbench documentation, which is very extensive and has a lot of comparisons for it. If you don't want to use these other, like if you're going to use only one popular open source tool, I would say sysbench is the one to start with because it does the most things and it's very well known. Postgres pgbench is this database micro benchmark that does a lot of random reads and writes. But one of the things that I can use it for that is not available through sysbench is I can also time the amount of time it takes to build the initial test database and use that as a bulk load test. And so that gives me my information on sequential reads and writes. The CDB workloads, they had a whole set of database micro benchmarks. Bank is a lot like pgbench. TPCC was a more complex sort of lock-bound workload, and this is something you encounter. Lockbound workloads, I think, is something that are fairly unique to the database world, and those are workloads that really scale badly, because the more processes you add to them, the more locks they have. And TPCC is a good example of that, but it also has to measure latency. Now, one of the other things I have to caution you, again, with doing this is, when you are doing your own benchmarking, which is the purpose, part of the purpose of this talk is to get you to do your own benchmarking, right? Because I'm going to show you what happened on my system, on my cluster, but my cluster is not going to be set up exactly how your cluster is. And so you need to test on your cluster. And one of the things you need to remember is you need to do a bunch of runs. Like, don't just do one test run on each configuration and assume that information is good. No, you need to do multiple runs and like average them or whatever. They need to be long runs because there's a lot of things like file caching effects, et cetera, that behave very differently with sustained activity. Ideally, you need to use multiple file and database sizes. You want a realistic level of work. So a whole bunch of client connections like you would have during peak load in production. And then I'm going to actually say, if possible, like if your goal is to test the software, then you actually want to do it on bare metal and not on cloud. Now, why would I say that? It's obviously easier to test on cloud, right? You can spin up as many AWS instances as you can afford to pay for and do it in a few minutes, right? Huge advantage. However, there's a problem with that, which is on any public cloud, you have this problem called noisy neighbors, where other people are doing resource-intensive things on sharing the same physical hardware with you. And the important thing is you don't know how many people and how much activity they're doing. And so often what looks like a difference in performance is actually a difference in overall cloud load. So if you are running this on bare metal, you can do fewer runs and have more consistent information. Like, and the difference is, for the benchmarks you're about to see in bare metal, I ran each one like 5 to 10 times. For the cloud stuff that I've done, I have to run it 25 to 30 times over a period of days, because I have to make sure that I'm not getting stuck in, say, a bad rack in Amazon's data center somewhere. So you can also do larger sizes because, I mean, let's be frank, 128 gigabytes of memory in your own hardware is like a bare minimum for a server machine, whereas it's very expensive on an AWS instance. So all of those prerequisites out of the way. Does anybody have any quick questions about the sort of parameters of benchmarking before I go into results? Go ahead. Yeah.
Bring you the microphone.
Like tools you're using, they're obviously like you didn't write them, we didn't write them, and we don't know all the.
Okay, hold on.
So the tools that you're using, you didn't write them, we didn't write them. We don't know exactly how they work, and so it's possible there's like CPU pegging or NUMA problems or like any number of things could be causing contention rather than actual storage issues. How do you like isolate?
Well, that's the reason why I strongly recommend that you use open source benchmarking tools and not closed source ones, because then you can actually look at what the code is, because absolutely that has happened with benchmarking tools. And it's not necessarily intentional on the part of the benchmark designer. They just took advantage of what seemed like a shortcut to them and ended up, for example, pegging all the activity on CPU 1. But that's why you need to use open source tools so that you can actually look at that. And that's actually also the advantage of using some of these older, better tested tools rather than the brand new ones. I mean, that's the disadvantage of using something like, say, the CouchDB tools or the MongoDB YCSB benchmark, which I do use because it tests a different use case, is that they're just very new, and some of those issues have not necessarily been worked out. And you might have to work them out. Okay, so let's talk about some results for comparisons. So one of the things I want to caveat here is that people like to want to publish results and stuff. You know, if you're going to go for a benchmark publication, there's a whole long process for that. I used to be part of an organization called the TPC, and it would take like 6 months to do a benchmark because we had to make absolutely sure that the results that we were getting were comparable in an absolute way. None of the results that I'm giving you are comparable in an absolute way. The different tests are not comparable with each other because they have different code and different parameters. The different databases are not comparable with each other because that wasn't my goal. You can set it up so you're benchmarking databases against each other, but that wasn't what I was doing. The databases that I'm using here are minimally tuned, basically out-of-the-box configuration settings, which is not ideal for database testing. But again, I wasn't looking to test the databases. And of course, my hardware and software is going to be different from yours. So let's talk about the hardware that I was using for this. So I have a 6-blade cluster in Red Hat's open source lab. Each of these blades has 20 cores and 128 gigabytes of RAM, and 2 SSDs that are 200 gigabytes-ish each, and a shared network. Now, this setup immediately puts some limitations on my testing. First of all, one of the things I really like to do is I like to test a workload with a small database, and by small, a database that is substantially smaller than RAM. And then I like to test a database that's big, which is a database that is substantially larger than RAM, to force things like swapping on the system. And because my RAM is almost as big as my storage, I could not really do the second kind of test. I kept running out of disk space when I tried. I am going to reconfigure these machines so that I can actually do that kind of test, but I haven't done it yet. The other issue that limited me was the shared network, which I will talk about in a minute. But what this means is, because my databases all fit in memory, it means that my primary limiter was going to be file sync I/O rather than raw write speed. Now, synchronous I/O is what you do in order to make sure your data was saved to disk, right? Lots of applications do this when they need to know that the data got to disk. All transactional databases do it. A lot of storage systems that care about missing data, like video systems, do synchronous I/O in order to make sure that it gets to disk. So it's an important thing to test, and that is what I ended up testing for a lot of these. Now, shared network also was an issue, like I said. So now, my first test is what I call the bare metal test, which is a pure host file system, as in Kubernetes was installed but not running. And I ran the benchmark client and the database on 2 different machines, 2 different blades, not in containers or anything. And so this is to get my reference number, right? If somebody is looking at migrating from bare metal from own bespoke server to running on a Kubernetes cluster, that's the comparison they want to make. And so I wanted to make that comparison. For anybody who cares about this, using XFS on LVM for file system, et cetera, obviously, as always, has some effects, but it's a fine combination as far as I'm concerned. So, I'm going to give you the grid layouts. So I'm going to show you a set of results for these, and I've put them in grid to make it sort of easy to visually compare them. And so this is for the sysbench, and I'm just using the sysbench file I/O test in order to do a random read and write combination, sequential read, sequential writes in this grid. So for the raw system here, these are again large memory, SSD storage, random writes very fast, random reads. Both random reads and writes are very fast. Sequential reads are really, really fast. Sequential writes were not very fast for reasons I still haven't determined. I actually ended up doing this so much as, in fact, reformatting one of the machines, reinstalling the OS and stuff to figure out why this is going on, because that's a low number considering the hardware that I have, and I have not yet figured out why it's that low. But this was the purpose. This was to get comparisons. Now, here's a second grid here, and this is 3 of the benchmarks, database benchmarks. So we have pgbench across the top. We have the bank benchmark with CockroachDB, and the TBC benchmark with CockroachDB. And I didn't actually say earlier, one of the other reasons I want to run the CockroachDB benchmarks is Postgres is a single node database or a fully replicated database, whereas CockroachDB is a sharded database. And so there's obviously some different performance there. Single node databases have more limitations on how much they can scale up in terms of CPU and storage, et cetera. Sharded databases use a lot more network And so you want to test both of those cases. So we did bank and TBCC on CockroachDB. Now, for pgbench, we did a simple thing, DB load time to look at a big sequential write, transactions per second, and average latency. Bank is actually kind of the same things. The nice thing about the bank test with CockroachDB is it actually gives me a percentile instead of an average. And a percentile is always better because SLOs and SLAs are generally expressed as 95% of transactions must complete within X. And so that's the number you actually want to know. Now TBCC, that new orders per second you'll see doesn't change much because, again, this is a lock-bound workload. And so that number only changes if the actual storage or memory or whatever hardware is slower than clearing the locks because people are not allowed to buy the same merchandise at the same time, right? For obvious reasons, right? It's an online store, you run out of things. So you have a real problem if you don't meet the SLO for new orders per second, and you'll see it actually doesn't change a whole lot in this particular run of tests. So, for bare metal, for pgbench, 404 seconds to load the initial database, including index builds. So that's my bulk load time. 11,000 odd transactions per second, a 2.8 millisecond latency. Now we've got a blank right here, and what's going on there is I have a fair amount of experience running CockroachDB on Kubernetes. I don't have a lot of experience running CockroachDB off of Kubernetes, and the numbers I was getting running it on bare metal were so bad, I clearly set it up wrong. So I don't want to share those numbers because they're not indicating anything. So I'm going to compare against the different Kubernetes configurations for CockroachDB. So we're going to do our first comparison. So there are a couple of different ways to use local volumes within Kubernetes, where what you're doing here is you are attaching local storage, local to the node something is running on, directly to the container running within Kubernetes. Local PV is the more sort of sustainable way to do it. There's still a bunch of it's a relatively new feature though, and so there's some kinds of storage it doesn't work with. And so some people are still using the older hostPath, which is harder to manage, which is why you want to use local PV if you can. These are two different sort of Kubernetes constructs. Basically, these are just local storage via container. So theoretically, since a container is just an abstraction in the Linux kernel, it's not a real thing, theoretically this performance should be nearly identical to bare metal performance. Let's see if it is. Well, for the raw file I/O test, it is, right? Less than 1% difference with anything, which is, so you can see there, and given the amount of variance in these tests, less than 1% difference really means no difference at all. The tests are not that consistent that you can actually measure at that level. Now let's see the database tests. Now that's a little bit different. So we did have a longer amount of time to do, we had 10 to, you see here 17% difference on the Postgres test. We're also getting some establishing numbers here for CockroachDB because now I've got a CockroachDB cluster running, so we've got our establishing numbers there. So what happened here, right? This should theoretically have honestly been, the same as we saw. The raw file I/O was not really any different, so why was the Postgres result different? Well, so the thing was, for my bare metal establishing thing, the client, the benchmark client, was not running inside Kubernetes. It was running on a host machine. So to make it comparable, I have the benchmarking client running on a host machine in this test. The problem with that is this means I'm going through some simple Kubernetes load balancing called NodePort in order to actually connect to the backend database, and this means at least one extra network hop, unless I'm lucky. And you see here the big jump is latency, And pgbench, because it does a lot of really small transactions, latency, it really dominates the benchmark because it's sending all of these little tiny short commands with no batching. And so, but it waits for a command to come back right before it sends the next one. So that network latency hit me particularly because, remember I said that all of these blades were on a shared network, shared with everything else in the rack with them. Well, this is also hitting me at this point because my network for Kubernetes internal communication and the network for the benchmark client communication is the same network. And so it had an amplified effect here. Now, our third configuration that we're testing here is our cloud-native storage using Rook and Ceph. So we've got 5 nodes of Rook and Ceph here. Now, because it's such a small cluster, I only did 2 replicas of each shard of the storage. Normally, for production thing, we have a larger cluster. You would do at least 3 for failure things, but it seemed ridiculous to do 3 when we only had 5 nodes to choose from. I did do some default tweaks that are in the Ceph documentation for performance. And the other important thing is I'm going to show you CockroachDB. So this is CockroachDB running on top of Rook Ceph as its storage, not Rook controlling CockroachDB, which is another option and is the sort of more mainstream one. Because one of the questions you would ask is, hey, if CockroachDB is a sharded replicated database, why would you put it on sharded replicated storage? And the answer is you really probably wouldn't, except for certain special circumstances. The reason I did it in this case was it showed something I wanted to test rather than something that was a likely production scenario. So we're going to go sysbench, and now we see some differences in raw file performance. So random reads and random writes are down a minority percentage, but still a noticeable amount. And again, this is some latency. Every time I write something, it's being written twice synchronously, and so we've got extra network latency, et cetera. So those are actually pretty good numbers if you consider that. Not a lot of difference in terms of reads, which makes sense. And my sequential writes actually went up. And I had to delve into this some. And it turned out that the reason for this was because it's sharded storage and because I was sequentially writing a substantially sized database, the chunks of the database were actually being written to different machines. So I, in fact, gained performance by having the database sharded in this particular case, or having the files sharded. Because what sysbench does is it writes a bunch of chunks, like 1 gigabyte chunks, and it writes a whole bunch of them. And so what happened was the different 1 gigabyte chunks were landing on different physical machines, which meant that whatever that 88 megabyte cap was with these SSDs, I was able to exceed that limit. So sometimes using using this advanced storage actually benefits you performance-wise. Now let's look at some of our database benchmark results here. Right. So now we see a bunch of extra overhead, right? We've got about 28% longer for the bulk load. A substantial, basically what we see consistently across this is our latency doubled for all of the sort of database workloads. And the things associated with that latency were cut in half. So latency doubled, throughput got cut in half. And this actually makes sense, right? We're writing everything twice that we weren't necessarily writing twice before. We're writing it twice as much in the case of CockroachDB. So we're doing twice as many synchronous writes with a minimum of 1 extra network hop. So, and I'll actually tell you, I've been testing databases on distributed storage since the days of MooseFS. Anybody remember MooseFS? So there we go, a couple of people remember it. So since the days of MooseFS, and these are actually really good numbers. Because if you think about it, how many databases do you have that actually are already twice as fast as you need because your expectations aren't that high, right? My Postgres, MySQL, a lot of CockroachDB databases now are actually really, really fast and often not the limiting factor in overall performance. And so this can be acceptable, but it can be not acceptable if you actually are hitting that limit. So some of the other things I'm tinkering with here is, and actually if you look at one of the KubeCon archives, look for, within the KubeCon YouTube stream, look for a presentation by a company called Percona. They went ahead and compared the different overlay networks. For this, I was just using the default overlay network for OpenShift, which is Open vSwitch. The different overlay networks actually turn out to make a huge difference in performance, and so do look for that presentation by Percona. I'll sum it up with 3 words, which is don't use flannel. I need to reconfigure the storage so I can actually do bigger databases. I distribute workload over CockroachDB better would be nice. Problem is with CockroachDB becoming non-open source, I'm probably going to stop doing testing on it, which is a shame because it was super useful. And of course, ask the Ceph guys to do some Ceph tuning to see if it makes a difference, except that, like again, from my perspective, Ceph was performing so well, I almost don't feel like it's worth doing any tuning. So, some conclusions here before we go to questions. Number 1 is benchmark your own hardware with simple database benchmarks to test your actual cluster performance. Second is local volume performance can be equivalent to running on bare metal if you're looking at moving to Kubernetes. So if you're willing to deal with local PV, et cetera, if you're performance constrained, that's actually probably the way to go. If you are not that performance constrained, Rook-Ceph has good enough performance for non-constrained applications while giving you a lot of sort of redundancy, et cetera. A couple of others. Also, beware secondary issues that look like key performance differences. Like sometimes your performance difference isn't coming from where you think it is, like my issue with using NodePort and the network between the benchmarking client. And then an extra tip that I'll say, because I didn't have my cloud slides in here, is on public cloud, one of the other things you'll discover is that public cloud latency effects, which are large, can mask any differences in performance that you're attempting to test. So, I am ready to take questions. And like I said, you can ask questions about the cloud stuff. I just don't have it in the slides, but we did do a whole bunch of testing.
Tell us about the cloud stuff.
Tell us about the cloud stuff. So to do the summary is we did so first I did a big test run just using a bunch of Amazon instances using pgbench and sysbench. And one of the things I discovered is using EBS natively, so using EBS via hostPath, versus using EBS via the Amazon CSI driver, there was no difference. So there wasn't a good reason to use hostPath for EBS volumes, since the CSI driver does a lot of failover management, et cetera, that you lose when you're doing local PV. So if your data is going to be in EBS, you want to use the Amazon cloud provider stuff for the EBS storage. We did discover that, then we did a bunch of Ceph Rook stuff, we discovered that whether it was better, if your data needed to be redundant, whether it's better to use EBS and rely on Amazon's redundancy versus using local ephemeral volumes but redundancy via Ceph and Rook on your own is workload dependent. There are workloads where EBS is cheaper and more reliable, and there are workloads where Ceph Rook is cheaper and more reliable. And to get more into that, I have to get into the numbers, but it's a sort of reasonable trade-off. We're going to actually, Saggy and I are going to blog about that particular issue, because we've also done cost comparisons, which are obviously a big deal in the public cloud. That's sort of a summary of the cloud stuff. More questions? Are there any limitations on the size of a database in Kubernetes? There aren't any specific limitations. The one thing I will tell you is Kubernetes thinks of itself as a sort of multi-tenant system, and therefore when you get to the point where a single pod is going to be using more than 50% of the resources on the system, you find yourself having to tweak Kubernetes for a lot of non-default behavior. So my general advice for people who say, should I run my database on Kubernetes, is to the extent that you have a lot of small databases, yes. To the extent that you have a few really large databases, no. Unless those databases are weird distributed sharded databases, in which case you can go back into Kubernetes land simply because for some of the sharded databases, Kubernetes effectively makes a great installer. Other questions?
I don't know if you said this, but is your database inside a pod inside the cluster, or is it outside of the cluster?
It's in a pod inside the cluster.
Oh, okay.
I did not test having the database as an external service and to see if that made any difference, mostly because I didn't expect it to make any difference compared to a completely non-Kubernetes test, so I didn't test that. Oh, hold on just a second. The mic is almost at you. Thank you.
You mentioned the noisy neighbor effect on cloud systems, and you also mentioned that I think you mentioned that you had done multiple runs on cloud systems. What sort of variance would you see between the runs at a maximum? Like
up to 3,000%.
Ah, okay.
If you actually look, I don't know, like scale 15. I actually have a talk, that was recorded for scale 15. On running databases on public cloud. Shootout in the AWS Corral. And I actually go over some of I have distribution charts for the distribution that actually led to a whole line of business for us in my old company, where we would actually run micro benchmarks on AWS to locate good instances for our customers. It was a moneymaker. Amazon actually kind of got wise to people doing that, and it stopped being quite as effective. But I mean, really, we would literally have a 30x difference between the worst performing instance and the best performing instance. And so when I was doing benchmarking on public cloud, what I actually did was a two-stage thing, right? Which is you do a whole bunch of runs, you do like 25 runs over a period of time. Because what happens is if you request a whole bunch of instances in a row, most of the clouds tend to basically stick them on the same machine. So over a period of time, and then you eliminate the outliers, which can be deceptive, right? Because you never know whether the outlier is because of a real problem or because of the cloud. And so I hate eliminating the outliers, but the outliers are so far out that I had to do it. The upside, by the way, is sometimes, if you're lucky, you can get spectacular performance from the public cloud. And on AWS, I know that's what happens is you effectively landed your instance on a brand new machine attached to a brand new storage volume that nobody else is using. But it's hard to depend on that. More questions? I have not. I did a lot of testing on Power 8 systems back in the day. Maybe Liz and I will team up and try this out on a Z series.
Once you have all the results, what's
you got a mic there. Go for it.
What's a good way to present the results so that they're easy to consume, like people that aren't?
Well, I mean, obviously, I like those charts, right? Because I'm trying to show differences and that sort of thing. If you do a whole bunch of test runs, graphs are nice. The important thing is to always explain what the numbers are specifically showing, because there's tons of combinations that you can do for different stuff. To the extent that you can relate a benchmark workload to a real-life workload that you know you're going to need to do, right? You say like, hey, we do video streaming, and so I did a bunch of sysbench and pgbench, sequential read and write tests, because that's similar to what we're going to have to do. Then that's going to be better. Because, I mean, here's the thing is, right, if you do pgbench and you do a transaction test, that's going to tell you nothing or very little about that cluster's ability to handle a large, sequential activity like file sharing or something. So, beyond that, it's all, just sort of data visualization. And I tried to show here is that sometimes that's a graph, but sometimes it's other things to give people an idea.
I think that's it. So,
Oh,
one
wait,
more.
one more.
Yeah, let me bring this.
So you say your databases were minimally tuned.
Yes.
Do you think the results might have been different had they been, better tuned? And what database were you using for the test?
Well, so the two databases were PostgreSQL and CockroachDB. I don't think so Postgres actually has a lot of automated testing done. And so the default configuration, while it might not be great for a lot of real-world circumstances, does really well for pgbench. And so that's one of the reasons why I didn't feel like I needed to tweak it. Because one of the things that Postgres makes you tinker with is actually directly telling the database how much RAM you have available. Well, pgbench doesn't actually make use of large chunks of RAM, so it doesn't make a difference. So the CockroachDB's default configuration is a lot more tuned than, say, Postgres or MySQL are out of the box. So again, I didn't feel like I really needed to touch that. There was one setting I changed. I don't remember what it was called, but it is directly off of, they have this big page of, if you're running CockroachDB on Kubernetes, here's some settings that we recommend you change.